So for those of you who participated this the previous session, they went through this 5G xHaul. And at this year at the EANTC, we actually did a combined use case testing where we actually put everything together here that we will show here. So I will not go through the details on the services side. That was gone through and presented in the last session here. But what we have put together here, and this is similar, very the same as the last thing, is that we put together the core aggregation access layer and simulating the 5G xHaul topology. All the devices here that we focus on was enabling and the timing and synchronization in the network. So all the devices you see from the different vendors are running as boundary clocks there. So we have a number of boundary clocks here. We have the grandmaster here, and we have simulation as well. So we simulate the RU, the DU traffic. We have background traffic from the down in the right and to the left. So we have background that we're sending through the network. And as well, as you see, we have multiple of timing test equipment devices in the network to measure the SyncE and the PTP performance throughout the network. So how we set this up is that we have this chain of boundary clocks from the grandmaster out through here. So they're all doing full timing support. It means that we are using the G8275.1 profile in the hybrid, where we are both running SyncE and PTP throughout the network here. We are using the telecom profile, and some of the SyncE performance there you're also having with the enhanced SyncE here. What you see here is that the traffic is simulated with a lot of background traffic, with also the RU-DU traffic, but as well having the sync going over with the services here. So what we do here in some of the test cases is that we have a congestion on a link between two devices in the topology, and we wanted to see if PTP and the performance of the synchronization were affecting here. So that was one thing here. Another thing was really to showcase the use of passive port monitoring feature, and the use of that is really to have a view on the performance and the offset between two ports on a router, on a boundary clock. Because in this case, we have all the test equipment here, but in the live network, we don't have test equipment out on every boundary hop in a chain. So this passive port monitoring feature is really a nice way of watching and monitoring the offset between two ports and see how that node and the performance is going through the network here. And of course, we have the test equipment here that we will come back and show really the performance of the setup here, where we measure the two-way time error and as well the relative time error out in the network here. So this was the background of how we will do it. So now we'll hand over to Gadam that he will show some of the output on his device here. So Gadam.
Thanks, Bronner. Hi everyone, thanks for joining the session today. Now let's see some of the show CLIs in one of the Cisco 8011 router. So in the upstream, we are connected to the different vendors like Raisecom, Ciena, and ZTE. And on the tester side, we have the connections to the Calnex and the Keysight. Now let's see some of the outputs from the what we are getting from the upstream and what profile we are running here. Yeah, if you see from the show LLDP neighbors in the upstream side, I am getting the signals, the timing signals from the ZTE, Ciena, and Raisecom. So if you see the PTP interfaces, now here my slave interface is 100G001, where I am getting the clock loss 6 from my upstream Ciena router. And if you see the show frequency synchronization interfaces brief, here we have selecting the 100G001 as my primary reference on my device. And on top of it, you see the PTP foreign masters. So I'm getting the clock signals from the 3 devices, and based on the received clock properties, my BMCA, which is running on my slave interfaces, that is selecting the best master from by reviewing all the received clock properties. And you can see here show PTP platform server. Now I am my router that is phase clocked to on the interface 100G001. And you can see the phase alignment accuracy is around -1 nanosecond. And these are all the received timestamps from my upstream. You can see the T1, T2, T3, T4. And based on that, my device is capable of calculating the offset from the master, which is like 1 nanosecond. And you can see the mean path delay. This is around 279 nanoseconds. And this is the passive port monitoring feature, which will measure the offset, the phase offset from the different masters where I'm getting the signals from the upstream. Now here I have the three ports which are enabled with the slave, and I'm running the G.8275.1 profile with the sync is enabled on it. Now here you can see this is the port 100G001, which is the primary port, and where you can see the offset is the 002 nanoseconds. So here, again the BMCA is the plays a vital role here, the choosing the best master, and this is the feature, the passive port monitoring, which will give you all the different phase offset from the different ports which are enabled with the slave mode. And this is the show PTP dataset performance clock. So this will give you the PTP performance measurement results. So from here, you can see the performance monitor dataset. This is for the current 15-minute window. So clearly you can see my device, the 8011, which is 3 steps away from my main grandmaster, which is the microchip here. And you can see all the master slave delay from the upstream, and this is the slave to master delay, which is calculated from the downstream, and you can see the mean path delay and the offset from my master. And now, after locking to the one of the upstream router, now I am advertising the clock loss 6 to downstream, so that the tester can measure all the end-to-end results, like mean time error and the relative time error between the 2 devices. And now I am handing over to the Neil to show all the test results.
Thanks, Gaurav. So Gaurav has showed what his device is reporting, what the sync chain looks like. What I'm going to do now is show you, show you some measurements that we can make to confirm the performance of our sync chain and also the protocol compliance. Because what we're demonstrating here today is obviously network performance. Without protocol compliance, the devices don't talk to each other. None of the synchronization would actually work. So we can see here on my first Paragon Neo, we've got 2 PTP sessions in running. If we first look at the protocol, what we can see here is we've got PTP exchanges that are conforming to the hybrid profile, G8275.1, that Bjornar mentioned in the first part of the presentation. And if we look over on the right-hand side here, we can see the GM clock ID and the steps removed. And this is showing here that we're measuring from an HPE device at the start of the chain, and we're also measuring from Garam's Cisco device at the end of the chain, where the steps removed is 3. So what this is showing is we can actually analyze the announce message parameters to confirm the sync chain is as we expected. Once we know that's good, we can actually look at our time error performance. And what we have here is the raw two-way time error from both the Cisco and the HPE devices. So the HPE device is locked directly to the Grandmaster, and we can see we've got good, stable time error performance there. The Cisco device is locked through an intermediate, and we can see a little bit more variation. And obviously that would be expected because the time error accumulates through the network. We can then look at this in terms of the actual standards-based requirements. So we have a topology that looks a bit like an ORAN network. Okay, so we have time error requirements that are defined there. So overall, end to end, we're measuring an absolute time error accumulation that needs to be less than 1.1 microseconds, plus or minus. And you can see we're really well within that limit there. We're measuring an average of around minus 20 nanoseconds. We can look at other parameters as well. So our SyncE performance, we can see our QL value, which means we have our traceable SyncE path, which is necessary to support our hybrid PTP profile. And we can see that we're meeting masks for that whole chain as well. So we have a Microchip grandmaster acting as an EPRC. We have our limit here, and our measurement is significantly lower than that. This is proving the devices today, albeit in a relatively short chain, are very capable of meeting the limits that are defined for telecoms networks. If we then look on our other device, we have connections to 2 endpoints. So this is relative time error, effectively measured at the ORU UNI. So again, we can check that on our steps removed. We have 3 on each of these, because these are both end-of-chain devices. And we can then look at our time error to confirm our two-way. Our clock class is good, so we're locked to the GM as expected. We're meeting our end-to-end requirement, but also, because we're looking at 2 ORU inputs here, we also have a time error relative limit between them. Tightest case for an ORAN topology is 60 nanoseconds, and we can see here we're still well within that, despite having 2 synchronization chains to separate devices. Okay. What we've also got is the Keysight TSA. So this is also measuring 2 endpoints higher up in the topology, and we can see here we get similar results. We have our Ciena device, I think it is here, measuring around 10. We had a small interruption. It didn't cause any operational issues because it's well within any limit that we might have. And the same on the other device here. We saw a similar interruption, but the behavior is still within any parameters that we need to define in order to make sure the network operates correctly. So with that, I'll hand back to Bjornar, who will just summarize what we've shown you today.
Hear me? Yeah. So this session summarized that we put all things together with all the services in the network, with the traffic that is required for our mobile network, including all the timing and synchronization, going over congestion's link as one of the links we're connecting. It shows that we are well within the limit of what the specification said, and we are seeing good performance here for both the PTP and the SyncE here. So thank you.